So you could even think of what we've learned about isomers is kind of this flow chart, because there's different types of isomers. So in general, isomers are compounds that have the same molecular formula, but they're different in some way. Okay. Well, one branch of this flow chart are the constitutional isomers. And so the way in which they are different is that they have the same formula, but the atoms are actually connected differently. We spent a whole lot more time talking about the stereoisomers. So remember, that's a situation where you have the same formula again, but at this time you also have the same connectivity. So you got a carbon connected to 3 hydrogens next to a carbon connected to 1 hydrogen and 1 chlorine next to a carbon connected to 1 fluorine and 1 chlorine. You see what I mean by connectivity? You got the same connectivity as well, but they are arranged in 3 dimensions differently. That's what makes a stereoisomer what it is. Okay? So the same formula and connectivity, but they're arranged in 3 dimensions differently. Okay, and so there are different types of stereoisomers. So this is where we've been getting into the weeds the past few days, and we will a little bit more today. You've got the enantiomers, which the only thing different is that it's a mirror image and it's non-superimposable. So they are unique molecules because you can't overlay one mirror image on the original. But then there's another type of stereoisomers that we call diastereomers. And so those they have the same connectivity, but they're not mirror images. Okay. And we looked into this a little bit before with our cycloalkanes, because you could have 2 substituents in the cis arrangement or in the trans arrangement. But more recently, we just talked about how you can have different configurations on the chiral centers. If you have multiple chiral centers, then you have multiple possibilities for how those chiral centers are arranged. It can be RRR, RSR, SRS. You know, there's lots of different ways that you can arrange the substituents so that you get the different chirality on the different chiral centers. So this isn't in your handout, but this is just something I want to talk through to kind of one more time explain the difference between enantiomers and diastereomers. Okay, so just kind of pay attention as I talk through this. So we'll say that compound A here, this is our baseline. This is what we're going to compare everything against, compound A. And so it has 3 chiral centers, right there where the fluorine is attached, right there where the methyl is attached, right there where the chlorine is attached. And if you figured out where or what those configurations were in this compound A, S, S, and R. Well, okay, so we can make the mirror image of that, and that's right here, okay? And so you can see it's the mirror image because what's close to the mirror is drawn close to the mirror, and then you just write it farther away as you get further away. So these mirror images are not superimposable. If you tried to pick this one up, if you try to pick up A and overlay it onto this one, it would not perfectly overlay. So it's an enantiomer. It's a mirror image that is non-superimposable, so that's the enantiomer. Everything only has one enantiomer. But remember, the general formula is that when you have chiral centers, the number of total stereoisomers is 2 raised to the power of n, where n is the number of chiral centers. So in this case, if it's 2 and there's 3 chiral centers, 1, 2, 3, 2 raised to the power of 3, so that's 2 times 2 times 2, which is 8. And so that's where we get the 8 different stereoisomers here. So one of them is an enantiomer. So the only enantiomer for A is what you see in B. So these are enantiomers, okay? And then everything else then would be considered diastereomers. So all these are diastereomers. Now they each have their own mirror image. That's why it's organized this way. Okay, but they are not anything more than diastereomers of compared to compound A. And so this kind of illustrates what I was talking about earlier. What makes it a diastereomer instead of an enantiomer is the way in which these substituents are arranged in space. So you notice that, like on the original, all 3 of these substituents point out. F comes out, chlorine comes out, the methyl comes out. Well, we didn't have to do it that way. We could have made the fluorine go in. So that's a different diastereomer. And then it has its mirror image. Or we could have made the methyl group go in, as it shows here in E. Okay, and it has its mirror image. Or we could make the chlorine go in, and it has its mirror image. So that's what we mean by diastereomers. It's, C and C through H here, they are not mirror images of A. There's only one mirror image of A. So there's only one enantiomer. But there are various ways that you can arrange those substituents so that you get different configurations, right? You can also, it's the other way you can compare. Like notice that this is SS and R, and this is SSS, or you could have RSS. So there's lots of different ways that you could arrange those those chiral centers. And so that's what gives you the diastereomers. Okay, so let me do some examples here. So what we're going to do is we're going to determine the relationship between these pairs of molecules. We're going to say whether they are identical, that's possible, whether they are some type of isomer, or whether they are unrelated. And if they are isomers, we want to specify the type. Is it a constitutional isomer? Is it an enantiomer? Is it a diastereomer? So let's look at these first two right here. So one thing if you notice is they look very similar, right? You've got the same connectivity. You've got oxygen double bond to carbon, oxygen double bond to carbon, which is connected to another carbon that's connected to a hydrogen and an OH, connect to another carbon, connected to a hydrogen and an OH, and on and on. So it's got the same connectivity. Okay. Well, if I were to, again, pick this one up on the, let's say that I want to pick this one up on the left here, and I want to overlay some atoms. I want to pick this up and, you know, overlay the oxygen there, overlay that carbon there, and the same thing with all the other atoms. What you would notice is that what would not match up is this OH would be pointing out, so it wouldn't overlay with this, with the OH on the other side. It would overlay with this hydrogen, and this hydrogen wouldn't overlay with the hydrogen on this side. It would overlay with the OH. So another way to think about that is that these two are mirror images. If you were to flip this one, or, you know, pick one, flip it around, you would see it's the mirror image of the other. Okay, so these are mirror images, and they're non-superimposable. So the name for that is this is a stereoisomer, and specifically it's an enantiomer. Okay. So just with these kind of questions, just take some time with it, analyze your two structures. Okay. So as I said, those are isomers, and the type of isomer specifically is enantiomer. Okay, so now let's look at the one right below it here. So in this case, we've got, you know, well, let's say there is a mirror here. Let's say that's a mirror. Okay. So there's a methyl group, and a methyl group, and a methyl group, and a methyl group. So these are mirror images, but also notice that if I were to pick this one up and try and overlay it on this one, they would match up perfectly. I could flip it around, and like this would overlay down here, and they're still both pointing out. And this, you know, I'm basically going to pick it up and kind of just overlay it right there, and it would match up perfectly. So that leads me to think that these two are actually identical. They are mirror images, but it's not a chiral compound. Remember, it's actually got that internal plane of symmetry. It's the same. If I cut it in half like that, it's the same on both sides. Okay. All right. And so even this one does have a chiral centers in it, like that carbon right there. It's got 3 different groups. Okay. If you look at the priority, that group right there would be priority 1 because it's got a carbon connected to let's see, 2 other carbons. Whereas this would be priority 2 because it's got a carbon connected to 1 other carbon. So that's priority 2. And this is the 3rd unique group. And then, of course, it's got the hydrogen that's not shown as well. Okay, so this would be priority 3, and then the hydrogen would be priority 4. So these are chiral centers, but it's a meso compound. So that's the other thing that we could, if we were asked to label it as a meso compound, you could do that in this case. Okay. All right, so those two are identical. So now I think I go up here to this box, butane versus methyl propane. Okay, so let's think about what that name means. Well, first of all, butane, if I were just to draw the skeletal structure, you got 4 carbons, 1, 2, 3, 4. And so the formula would be C4H10. Okay, well, 2-methylpropane, well, so there's my propane, 1, 2, 3 carbons. And on the second carbon, there's a methyl group right there. So that's got 1, 2, 3, 4. So this also has 4 carbons in it. And it's got 3 hydrogens on that one, 3 hydrogens on that one, 3 hydrogens on that one. So there's 9. And then there's 1 hydrogen that's not shown in the middle, the central carbon there. So that's, once again, 10 hydrogens. Okay, so they both have the formula C4H10, but the connectivity is different. So in this case, all the carbons are attached in a chain, a straight chain, whereas with the 2-methylpropane, you've got that branching. So this I would call constitutional isomers. These two compounds are related as constitutional isomers. Okay. And finally, we go down here to the final one. So we know they're not mirror images of each other. If you draw the mirror plane here, that they don't match up exactly, because here up top they match up because both of them are pointing out. But down below here, one's coming out. And so in the mirror image, it should also be coming out, but it's not, it's going in. So these are not enantiomers because one is not the mirror image of the other. Okay. And they are chiral. Again, we could look at how they each have 4 different groups attached to the carbons Once again, your chiral carbons, hopefully you're, a little bit more comfortable with that already, or at this point. But so there's a chiral carbon there. There's a chiral carbon there. Okay. So what these are, since they are related, and what their connectivity is the same, their formula is the same, but their arrangement in three-dimensional space is different. This one methyl group down here is going in versus coming out. What we can say is that these are isomers, but they are diastereomers. All right, the other thing I'll say about it is, you could figure that out also by, if you did assign configurations, you would see that the configurations on one is not the same or directly the opposite of the other. Okay, so those are diastereomers. Okay. All right, so now we're going to talk about the idea of prochirality. Okay, now that means something that's not chiral now, but it could be made chiral fairly easily. So it's a molecule that can be converted from achiral to chiral in a single chemical step. And so the example given to you there on the slide is that something that's not chiral, like 2-butanone. And remember, one reason why you could say this molecule is not chiral is because remember we said it has to be attached to 4 different groups. Well, this one's only attached to 3 different groups. There's no 4th group there. And that double bond to the oxygen, you could think of it as like, two bonds to oxygen. So that's why it is not chiral. It is achiral. But if we were to react this carbonyl group and add a hydrogen to it, and also put a hydrogen on the oxygen to make it, neutral, then all of a sudden it becomes chiral, because you've got 4 different groups. You got the hydrogen, you got the OH, you got the methyl, you got the ethyl. Okay. So the chirality of the product then is going to depend on which face of this carbonyl you react with. So it's kind of shown in this picture as a reaction coming from this direction. So think of that as like coming from above or coming into the screen from in front of the screen. But also the reaction could, it's going to be difficult to draw, to illustrate in 2 dimensions like this, but it could come from behind, okay, where you can think of this as like coming from the inside of the screen and attacking the carbonyl group and then coming out of the screen, right? So it's 1 of 2 different directions. So the reaction could occur either out of the screen going in or into the screen coming out. It can go in either direction. So which enantiomer of 2-butanol is produced depends on which face of the planar carbonyl undergoes the reaction. Okay, so that's one way that a compound can be considered prochiral. All right, so we have some labels for those different situations. So as I said, the planar faces that can become tetrahedral, so right now they're not tetrahedral, they're trigonoplanar, but when they become tetrahedral, they look different from the top and from the bottom. So the planar faces can become tetrahedral are different from the top or the bottom. All right. So these are very similar kind of annotation that we've seen before. Instead of R, it's RE, re, okay, the re face. That's if you're looking at the molecule and the priority goes clockwise, as you can see here. The highest priority would be the oxygen because it has the highest atomic number. And then the second highest priority would be the ethyl group because it's got carbon connected to another carbon. And the third priority would be the methyl group because it's just got carbon connected to 3 hydrogens. Okay, so since that makes a clockwise turn, okay, or a right turn, if you're thinking about a steering wheel, we call that re. All right, just like R was when that priority ranking led to a right turn, a clockwise turn. But then if you look at it from the other side, that would look counterclockwise. But the impact is, and you can see that over on the right here, that it determines whether you have an S configuration if you're coming from the re face. So that's kind of the little curveball that you got to remember. If the reaction occurs from the re face, it produces an S configuration. If it happens from the C face or psi face, whatever, it becomes the R configuration. All right, so the re face, the face on which the arrows curve clockwise, and the C face is the face on which the arrows curve counterclockwise. Or if you like the steering wheel analogy, clockwise would be a right turn, making a right turn, counterclockwise, making a left turn. Okay, here's another example. So we want to label these 2 faces of crotyl alcohol. Okay, so think about the priority of the groups that are attached to that carbon. That's how we're going to do this. So this is a carbon and connected to hydrogen. That's pretty low priority. That's really low priority. So we've got carbon connected to hydrogen, and we've got carbon connected to, carbon connected to carbon, carbon connected to carbon. So that doesn't make the distinction. So then I've got this carbon connected to two hydrogens and an oxygen. This oxygen is connected to that carbon, right? This carbon is just connected to a hydrogen and another carbon, okay? And another carbon, because remember, double bonds, you think of it as like independent bonds to a second carbon, just in an imaginary way. So the point being is that this is going to be my highest rank priority, okay? And then this is going to be my second priority, and this is going to be my third priority. So we get the clockwise turn if you're looking down at it from this direction. So if you're looking down from this direction, it goes 1 to 2 to 3. Okay, so that's where you get the clockwise. So this is going to be my re, and then by default, then the other direction is the C. All right. Okay, so one more example. So something you're perhaps familiar with if you like to work out, lactic acid, right? That's what causes the pain in your muscles after a workout. So lactic acid accumulates in tired muscles from pyruvate. This is a pyruvate three-dimensional ball and stick kind of representation here. So if the reaction occurs with the addition of H to the re face of pyruvate, what is the stereochemistry of the product? So I guess we have to decide, we have to look at this and decide which one is the re face, because this is saying that pyruvate becomes lactic acid by adding a hydrogen to the re face. Okay, so in order to do that, I got to come up with the priority of each of these, you know, each of these groups on this pro-chiral carbon. So this is carbon connected to oxygen. So oxygen has the highest atomic number. We got oxygen compared to carbon and compared to carbon. So since this oxygen has a higher atomic number, that's going to be ranked number 1. Okay, so then the next group, well, it's carbon versus carbon. Well, this is carbon attached to 3 hydrogens, but this carbon is attached to 2 oxygens. So that's higher priority because those oxygens have higher atomic number than hydrogen. So that gets the second priority. And then that means that the methyl group gets the third priority. Okay, so in what direction is it a re face coming, looking at it this way or looking at it this way? Well, it goes from 1 to 2, 2 to 3, and then 3 back to 1. That's going to be clockwise if we're looking at it from this direction. So a part of the reason why I do it that way and I put this example in there is because in the previous examples, it may look like re was always above, you know, up top, and Si was always from down below. That's not necessarily the case. It's whichever one leads to that clock. Re is always the one that leads to the clockwise rotation, okay, the right turn with the steering wheel, and then the C is always the one that leads to the counterclockwise rotation, or the left turn with the steering wheel. Okay, all right, so that's the point, is that the hydrogen then, the hydrogen is going to attack right there. And so when it does, what that is going to result in is that the hydrogen is going to attack there, and it's going to push the other 3 groups back. So those 3 groups are going to kind of go back. And so this, let me erase that one. Okay, so this is going to be an oxygen, and that's going to get another, so that oxygen that I just wrote is this oxygen right here, but you know, nature's not going to let it stay just as a negatively charged oxygen. It's going to throw another hydrogen on there. So this OH group comes from that oxygen right there. And then, okay, so that's like a single bond to an oxygen and a double bond to an oxygen. And then coming out is your methyl group, your CH3. Okay. All right. Well, once again, what I need to do is kind of imagine that, you know, I push this hydrogen back away from us. And so what would that look like on our steering wheel? If I put that hydrogen back away from us, then I've got the OH here. I've got the C, single bond O, double bond O there. And I got the methyl group. Now all these are kind of coming out of the screen at this point because I pushed the hydrogen away from me. And I got the CH3 there. So in terms of priority, this is 1, this is 2. Again, because the carbon, when you're comparing the 2 carbons, this carbon's got 2 oxygens attached to it, so it's higher priority. And this is a 3. So that's 1, 2, 3. So that's, you know, a left turn or counterclockwise. So this product is going to have the S configuration. Okay. So what is the stereochemistry of the product? It's going to be S configuration. Now, prochirality can also come from compounds that are already tetrahedral, sp3 carbon. Remember that tetrahedral geometry goes along with the sp3 hybridization. But we said so far up to this point that anytime you have 2 attached groups that are exactly the same, it's achiral, it's not chiral. Well, sometimes in certain circumstances, we can consider that prochiral. All right, and so now we want to talk about that. So prochirality is also evident when you have sp3 carbon with two groups that are the same. That's called a prochirality center. Okay, so how are we going to deal with this, or how are we going to identify, what's the difference between the two? The two identical groups are distinguished by considering either and seeing what if it were increased in priority in comparison with the other. Okay, so that's kind of an abstract sentence. It will make more sense once we do an example here. So here's the bottom line. If you, in your imagination, make that group higher in priority, and that turns the chiral center into R configuration, then we call it pro-R. So if the center becomes R, the group is pro-R. And just the opposite, if doing that, sort of theoretical, imaginary exercise makes the chiral center S, we call it pro-S. So again, if you look at this picture here, this green hydrogen we've labeled as pro-R, and the reason why is, but first of all, notice what we did here. We increased its priority just a little bit. It's still hydrogen, but we're calling it deuterium. That's what that superscript 2 on the left means, remember? And also remember, this is something that we put back in an earlier, I think it was in week 4, lesson 3. But deuterium, which is a hydrogen with a proton and a neutron in its nucleus, is higher in priority than just regular old hydrogen. Okay, so that's how that's how you can imagine this. You still consider it hydrogen, but make it deuterium, and then it becomes higher in priority. And the reason why you want to do that is because you also don't want to overcome the priority of anything else that is there. So you might be, well, instead of hydrogen, let's just make it a fluorine, or let's make it a bromine. Well, that might really change things because it might be higher priority than some of the other groups that are there. So the best thing to do is just to make it higher priority by just a little bit so that you don't overcome the priority of the other groups and change the rankings overall. Okay, so back to what I was saying. So if I change this green hydrogen to a deuterium, then look at what happens to the priority ranking again. So connection to the oxygen, this is the highest atomic number, that's still priority 1. Okay, carbon is a higher atomic number than deuterium, so that's priority 2. And then the deuterium becomes priority 3. And then this is going away from us, so I can just look at how that goes. So R, because it's 1 to 2, 2 to 3, right? That's a clockwise turn. That's a right-hand turn. So that's a R configuration. So that's why we call that one pro-R. And you don't even have to do the analysis for the other one if you don't want to, because it's just the opposite. Okay, if this one is pro-R, then the other one is pro-S. And it just happened that this was the easier one to figure out because this hydrogen, this blue hydrogen, is already poking away from us. It's headed back into the screen. Okay, so let me do this example here. So I want to identify the indicated hydrogens in the following molecules as either pro-R or pro-S. Okay, so let's do that. Okay, so here's my chiral center right here, my prochiral center right there. So again, the oxygen has the highest atomic number, so that's going to be priority 1. Okay, and so then this over here has got a connection to carbon, so that's going to be my priority 2. Okay, and so let's say that this one is the one I'm going to make it a deuterium. We're going to call that one a deuterium, so that's why I put this superscript 2 on the left there. So now it's a higher priority than this hydrogen that's poking back into the screen. So that means that it is going to have a priority 3, right? Because deuterium has a higher priority than hydrogen, but the lower priority than carbon. So 1 to 2, 2 to 3. Okay, so it's like I'm making a left-hand turn, or it's going counterclockwise. So this one, that hydrogen right there, is pro-S. And if I did that right, then you don't even have to do the analysis again, because by default, then the other one is going to be pro-R. Okay, so let's do the same thing over here. So again, let's just kind of assign some priorities here. So this prochiral carbon right there, it's attached to a carbon, and it's also attached to a carbon over here. But this carbon that's in the benzene ring, that's got nothing but carbon and hydrogen in it. Whereas over here, this carbon has got, some higher atomic number atoms involved. It's got some oxygens, it's got a nitrogen. So that means that this one wins. This gets the highest priority. This group right here gets the ranking number 1. Okay. Well, this is benzene ring is going to get priority 2 because it's got carbon, and I compare that to deuterium, right? So that means that this is going to get priority 3. It's higher priority than just regular old hydrogen. And again, this is a what if scenario. We're just imagining this. What if this was deuterium instead of just regular hydrogen? It would get a higher priority than this hydrogen. Okay, and so then we're going 1 to 2, 2 to 3, Okay. And then 3 back to 1. But, oh, wait a minute. Yeah. So I believe that is also, because that's clockwise, right? Clockwise. We're making a right turn. So that means this one is pro R. And then again, by default, this is pro S. All right. So pro S, pro R, pro R, pro S. Now, why is this important? Why do you care? Well, we see this a lot in nature, actually. So it's worth talking about. Because stereoisomers are readily distinguished by chiral receptors in nature, be it an enzyme or some protein on the surface of a cell that's stereospecific. You see it a lot in nature. And so the result is that you might have a transformation rate specific to one stereoisomer that's accelerated. Remember, what enzymes do is they accelerate the rate of reaction. They don't, cause reactions that wouldn't otherwise occur, but they accelerate reactions. And so if the enzyme is stereospecific, then we'll accelerate the reaction of one stereoisomer and not others. And I like the way that this picture kind of illustrates that. So if you look, it's, kind of like those toys that you play with in preschool, that where you put the round peg in the hole, and you put the square peg in the square slot and things like that. So that's kind of the way that the active site on enzymes and cell signaling pathways, that's the way that they work. Due to shape and electrostatic interactions, it's kind of like square peg in a square slot, round peg in a round slot. So if you, and notice that these are mirror images of each other. These two molecules, they're chiral. One is the mirror image of the other, and it just doesn't line up. The triangle would be lined up with the cylinder, or the spherical one, and the sphere would be lined up with the triangle. So it wouldn't sit in the pocket. So this receptor, whether it's an enzyme or whether it's some protein on like the surface of the cell membrane, it's just going to interact with one of those stereoisomers and not others. So if this is an enzyme that's facilitating, if that's accelerating a chemical reaction, then what you're going to see is the buildup of the product of one stereoisomer and not the other. Okay. And this even can occur with prochiral compounds. So with some enzymes, even prochiral compounds transform at an accelerated rate into specific configurations. So you put in something that's not chiral, but you get something that's chiral out of a very specific configuration. And so again, you have a diagram on the right here of how that works. So the protein it might be an enzyme. Let's just talk about it like it's an enzyme. So that active site, that pocket that the substrate sits in, it's got the very specific geometry and intermolecular forces and things like that specify the substrate arrangement. So in this case, that red square-shaped peg has got to be there, and the yellow cone-shaped peg has got to be there. And so that means that only the pro-S hydrogen is going to go into the enzyme, and the pro-R hydrogen is going to be sticking out. And so that leads to a very specific activity, and it leads to a very, a product. The profile of your product is going to be chiral heavily in one stereoisomer. So that's what I'm saying here so with some enzymes, even prochiral compounds transform at an accelerated rate into specific configurations, and this will eventually lead to the buildup of one configuration over the others. Okay. All right. So one last thing to talk about before we call it good for today is that there actually are potentially other chiral centers than carbon. Remember that we talk about carbon so much because it likes to form 4 bonds, and that property of tetrahedral geometry is what enables chirality. Well, you could have tetrahedral nitrogen, but it's typically not a chiral center because it inverts itself rapidly. So you imagine this nitrogen in the middle, and you got these 3 different organic groups, 1, 2, and 3, but they just flip back and forth so rapidly that it really the chirality of it just doesn't show up. So it's kind of like this, this animation here of an umbrella. So think of the nitrogen is the middle of the umbrella, and the 3 R groups are the cover of the umbrella, and what's going on is what you see in this animation. So these R groups are flipping up and down, and that happens so fast that it kind of disallows chirality in nitrogen containing molecules. So theoretically, yes, but in practice, not really. Okay, but there are other elements that can have tetrahedral geometry. Phosphorus is one of those. So phosphorus can be a chiral center if it's tetrahedral. Phosphorus doesn't have to have a tetrahedral geometry, but when it does, it can be a chiral center. And the reason why is because it still inverts like the nitrogen does, but much slower. And when that is the case, when it is chiral, then interestingly, the lone pair of electrons gets the lowest priority. Okay. And that's because its atomic number is 0, right? There's no protons there, just a pair of electrons. And sulfur is the other one, but only when sulfur is in a sulfonium salt. Okay, so it can't be like with its bent configuration. It's got to be that trigonal pyramidal configuration, and that's only happening when it's a cation, a sulfonium cation. Okay, and these are actually pretty important because that one you see there on your screen, that's responsible in a lot of biochemical reactions to transfer that methyl group to some other substrate.